When you speak to the person next to you, the sounds you make travel through the air as waves and are picked up by the eardrum of the person listening. This diagram here illustrates how the air molecules, shown in green, how they move and vibrate can be represented as a sine wave, shown in blue. Okay, before we get into this, let's just have a look at the kind of questions you are expected to answer in your computer science GCSE. So, what effect increasing the sampling rate would have on a recording? So, you obviously need to know what is meant by a sampling rate, okay? And why would a sound recording with a high sample rate normally result in a better quality recording than one with a low sample rate? So you need to know what the difference between a high sample rate and a low sample rate is, and implicit in this is a good understanding of the difference between an analog file and how an analog file is sampled at a regular interval to create a digital recording. And finally, state one benefit and one drawback of increasing the bit depth of an audio file. So let's get into that now. An analog sound wave is a continuous sound wave. So if we were talking to each other face to face, my voice would be making vibrations in the air molecules that would be continuously picked up by your eardrum. Now, computers don't work quite like that. They need to sample that analog sound wave and convert it into a digital format. And what is meant by sampling? Well, basically, the analog wave, its wave height is measured at regular intervals. And in this example here, you can see that the digital sound wave roughly maps to the analog sound wave, but some data is lost. It doesn't map perfectly, it's not a perfect copy, and that's because it's been sampled at regular intervals. So let's have a quick look at two sampled digital recordings of the same analog sound wave. So this sound wave on the left is exactly the same as the sound wave on the right. But this one is a higher quality digital recording compared to this one on the left, which is a lower quality digital recording. And there's a couple of things that make the difference of how high quality that digital sampling will be. There is the sample rate and there is the bits per sample. So we'll explain that in a bit more detail now. First, let's look at the sample rate. So you can see on this graph that we've got a time scale along the bottom. This is time in seconds. So this audio clip is 5 seconds long. This sine wave is not stepped, it's an analog sound wave. And we are now going to sample that analog sound wave and convert it into a digital format. So the way a computer does that is it needs to measure the wave height at a regular interval, and that interval is called a sampling interval. So these vertical green lines are representing the sampling interval of 1, 2, 3, 4, 5 samples per second, and this is an incredibly low sampling rate, but for illustrative purposes we can see that every 1/5 of a second this purple cross is representing the measurement of the wave height at every 1/5 of a second, and the computer is not recording anything in between these gaps. Okay, so every 1/5 of a second it is measuring the height, the wave height, but it doesn't really know what's going on in between those sampling points. So we measure the sampling rate using hertz, which you may have heard of as cycles per second. So in this context, it's samples per second. So if we're taking 5 samples per second, that is 5 hertz. Obviously, in the real world, a CD, for example, takes over 40,000 samples per second but we're showing this in a simpler format to make it easier to explain. Now, one way to increase the quality of a recording is to increase the sample rate, and these green vertical lines are indicating that we now have a sample rate of 10 Hertz, so 10 samples per second. And as we start to measure the wave height represented with these purple crosses, because we've got more samples per second, we can closely map the analog sound wave with our digital file. So Hertz is a measure of samples per second, and if we increase the number of samples per second, we can get a better, higher quality digital recording of that analog file. So now we understand what sampling rate is, let's have a look at the sample resolution. So sample resolution is the scale we use to measure amplitude, and amplitude is talking about measuring the wave height. And in this example we've got quite a low sample resolution, so you can see the scale goes from 0, 1, 2, 3, and if we wanted to record a higher quality file we could increase the sample resolution, and in this example it goes from 0 to 7. Okay, so this is the part that always causes a bit of confusion. If we go back to the lower sample resolution, which is a scale of 0, 1, 2, 3, and if we want to measure the amplitude, the wave height, why can't we just put a cross here? Okay, so, or why can't, this one is almost on the line here, so that's about right, and this one's fine, but why can't we put a cross here? Well, we can't, and I'll explain why. Let's assume a sample rate of one sample taken every fifth of a second. Okay, so at 0 it's measuring the wave height, and then at a fifth of a second later it will measure the wave height, and it has to save a value for amplitude. Now we'll do this in binary and not denary, so let's put those in, and you can see here we've got binary values going from 0, 0 to 1, 1, representing these denary values 0, 2, 3. So how many bits do we need to store these binary values? So there's 2 columns, so we need 2 bits. And these symbols here represent the bits. So computers, as I'm sure you remember, are a giant collection of transistors, of bits, of switches that can either be on or off, can store a value of 1 or 0. And what we're showing here is that every time a sample is taken, every fifth of a second in this case, it is recording the wave height using 2 bits. So the sample resolution is 2 bits per sample, and that is measuring the wave height, the amplitude. So let's say that again. So we, every fifth of a second, which is the sample rate, we are measuring the wave height, the amplitude, and we are storing a value for that wave height, for amplitude, every fifth of a second using 2 bits, and that is the sample resolution. So how, as we said before, why can't we put a cross not on the green line? Why can't we have sort of a 0.5 or a half? Well, that is because, as I'm sure you remember, that a bit can store either a 1 or a 0. You can't have a half a value, and that means that with this sample resolution you can only ever record the amplitude, the wave height, as one of these 4 values. So in denary that would be 0, 1, 2, 3, and in binary this is what's actually being stored, 2 bits per sample, this value. So you can't have a halfway measure, it has to be on one of these horizontal lines. Now, we said before that if we wanted to increase the quality of the recording, the digitizing of an analog file, we could increase the sample rate, and that is being represented by this doubling of the vertical green lines. It's increased the hertz from 5 hertz to 10 hertz. And we can do the same thing with amplitude. So with an amplitude of between 0 and 3, it's 2 bits per sample. That is our sample resolution. Every time a measure is taken, it is storing 2 bits, 2 binary values. Okay, well, we can have a higher sample resolution. Okay, so now I've increased the sample resolution, and we've got a range of between 0 and 7 in denary terms. So how many bits per sample do you think that we need to have a scale of amplitude that involves between 0 and 7 in denary? Do you want to pause the video for a second and have a little think? How many bits per sample? What's the sample resolution for this scale? Here is the answer. So you can see that if we convert this denary scale into binary values, that to achieve a value of between 0 and 7 denary, we actually need 3 binary numbers, and that means that our sample resolution is 3 bits per sample. So let's keep it simple for now and have a 5 hertz sampling rate. So this vertical line is representing the sampling interval, that every 1/5 of a second a sample is taken. Now remember, we can't do a cross in between the green lines. Okay, so the closest one is here. So at 0 seconds, the value that is stored is 0, 1, 1. And then a 1/5 of a second later, the closest value that it can measure of amplitude of wave height is 1, 1, 0. And then we keep on going every 1/5 of a second, recording a value. So this time it's 0, 0, 1. And then we keep on going until we have sampled the entire audio clip, or 5 seconds of it. And every time the wave height is measured, is sampled, it is using 3 bits to record that wave height, to record the amplitude. So the sample resolution is 3 bits. Okay, we're going to look at those GCSE exam questions again in a minute, but just before we do, let's recap. So we know that an analog wave is continuous. If we're in the room together talking, your ear is continuously picking up how the air molecules are vibrating, and that a digital sound wave samples that analog sound wave so that it can, at regular intervals, measure and store the wave height. Now the regular intervals is called the sampling interval. Okay, so this is sampling at 5 samples per second, which is known as 5 hertz, and we could increase the sampling rate to 10 hertz or even 40,000 hertz, so to more accurately represent this analog sound file in a digital format. And the other way that we can increase the quality of a sound file is to increase the sample resolution. So we know that amplitude is the measurement of the wave height, and that if we have more bits per sample, we can have a finer scale. We can measure more accurately what that wave height is. So this is a sample resolution of 2 bits per sample, and this is a sample resolution of 3 bits per sample. So let's have a little look at these questions. So let's have a look at this first one first. Explain the effects of increasing the sampling rate on the recording. Do you want to have a little think? pause the video for a second and then we'll go through the answer. So to answer a question like this effectively, you have to sort of identify the key terms, explain what they are, and then explain the answer. So what is meant by sampling rate? Well, in these examples below, this has a sampling rate of 5 Hertz, so 5 samples per second, and then we doubled that to 10 Hertz, so 10 samples per second. So increasing the sampling rate will allow us to to sample the analog sound wave more accurately to produce a higher quality digital sound. So let's have a quick look at the actual mark scheme. So hopefully you did say that the sampling rate was more samples per second, and that the result of that was that the more accurately measuring the analog sound wave, which produces a higher quality recorded sound. And the other impact is because we are storing more data, because we are taking more samples per second, the file size increases. Let's look at another question. So this is very similar to the first questions we looked at, but can you please now answer this question, explain why a sound recording with a higher sample rate will result in a better quality video than one with a lower sample rate. So pause the video now, jot down your answer, and then we'll review it. Okay, and here's the answer. So hopefully you were clear in your definition of terms, and you explained that a higher sample rate is more measurements are taken per second, which means that it can more accurately sample the curves of the original analog sound wave, and that means there are less chance of missing parts of the original sound. Let's do another question. Okay, so this is the last question in this video. Pause the video now. Okay, so this is obviously a question about bit depth. Do you know what the bit depth of an audio file is referring to? Well, hopefully you remembered what we were talking about in the slides here. So a bit depth is about the scale used to measure amplitude. If you have a sample resolution of 2 bits per sample, you have a less fine-grained scale than if you have 3 bits per sample. That's because you have to record the wave height on these green lines. So if you've got a finer scale, if you've got a higher sample resolution, you can more accurately record the wave height. So how does that help us answer this question? So what's a benefit of increasing, of having a higher bit depth, of having a higher sample resolution? Well, a benefit is going to be that you can more accurately record the wave height of the audio file. And what would a drawback be? Well, a drawback would be that because you are using 3 bits every time you sample the wave height, you are storing more data, so your file size is going to be larger. And let's have a look at the actual mark scheme. So one benefit and one drawback of increasing the bit depth. Okay, so we know what bit depth is. Hopefully you did identify that increases the accuracy, and a drawback is it requires more data. There's more storage required. Now it's quite interesting that they've written here, do not accept increases the quality. So we've got to be quite careful with our terminology here. So when you are answering questions about bit depth, make sure that you are not just using vague language and saying that it's got a better recorded sound file. Make sure you're using careful language that identifies that you are more able to accurately measure the wave height. Great, well done. Okay, this video is about as long as it needs to be. You may need to watch it again though, and if you're not really confident in these key terms, you absolutely need to be checking your understanding of this. So for example, you should pretty clearly understand these definitions as they've been written here. Now that's because the next video we're going to talk about is going to be answering questions like this. So you need to be confident in those terms because you are going to be calculating the file size of audio files, and obviously you need to know things like sample resolution and the sampling rate as part of that calculation. So we'll look at that in the next video.